Thanks for joining us for 11 a.m. talk on cloud infrastructure from Python code. How far could we go? By Asher Sterkin. Asher is a 40-year industry veteran specializing in software architecture and technology. He currently serves as general manager and head of engineering of Black Swan Technologies BST Labs, which is developing the cloud AI operating systems at www.caios.io, cloud infrastructure that incorporates infrastructure from code. Prior to this role, Asher served as a distinguished engineer at Cisco and currently lives in Tel Aviv, Israel, with his wife Irina and two Boston Terrier pets, Ockley and Molly. I also want to add this is a live remote talk, so if audio is muffled for you in person, if you have difficulty, recommend watching the captions in the Fletcher Theater, or you could also watch YouTube stream on your device, on silent please, to read the captions. And yeah, handing the microphone over to you, Asher.
Hello, everyone.
Hello, hello.
Hello. I'm Asher Sterkin from Black Swan Technologies Tel Aviv, and I will be talking about generating cloud infrastructure templates directly from Python application code, focusing on strategic potential of that technology. A couple of things I have to say about myself. As already Jeremy said, I'm a software engineer for many years. Some people do not believe it's possible to survive so long in our profession. Here are my social contacts. You could find me, and the slide desk will be uploaded to SlideShare. Disclaimer, I could not be completely objective because I'm one of the vendors in this field. I will avoid any direct marketing against sovereign competitors. I'm not representing my employer, and I do not get any commissions from AWS. AWS icons are for illustration purposes only. So let's start with trying to figure out what the mission of infrastructure from code, what we're trying to accomplish. I would say we want to democratize cloud programming, make it accessible for mainstream Python developers. Not only writing code, but also deployment operation with ease of use, frictionless, while preserving core security, reliability, and sustainability. That basically assumes that we treat cloud as a supercomputer. And I wrote an article on this interpretation of cloud technology a couple of years ago. You could find it here. Now, to implement this mission, to accomplish this mission, we adopted so-called mullet architecture, first introduced by Tim Wagner, the inventor of AWS Lambda. It basically says we will preserve familiar exterior of the system and completely renovate interior. That kind of double structure. I personally currently live in a Bauhaus in Tel Aviv under UNESCO protection, so I could really first-hand experience this preserving exterior and renovation of interior. What's wrong with existing state of affairs? In spite of many years of efforts in DevOps movement, we have two silos. We have somebody who writes code using Cloud Platform SDK, for example, Boto 3 on Amazon, or Cloud SDK of Azure, or GCP, or whatever. And we have somebody, sometimes called DevOps engineers or template writers, or whoever they have names, who package, deploy, and operate, and they use YAML or JSON files, speak different language. And these two groups do not understand each other. There's a lot of throw-the-wall interactions. The both sides are low level of abstraction, hard to master, takes long time to learn, and they pretty far from core business. If you need to generate financial reports or even process some IoT signals, dealing with low-level nuts and bolts of cloud is very far from that. I mean, big mental debt. There was a recent movement presenting cloud infrastructure or wrapping it in a mainstream programming language. It's called Cloud Development Kits. Some of them are more portable, for example, Pulumi or Terraform CDK. Some of them more platform specific, like AWS CDK, but they do not solve the problem. They just, like a macro assembler, wrap the same low-level concepts in the mainstream programming language, but the gap remains there. It doesn't solve it. How we do it? We need to raise the level of abstraction and bridge the gap. That's the approach. How we do it? We follow 12 points of application architecture. We keep logic and configuration separate, but we express them at high level of abstraction. At the application logic level, we could speak in terms of standard APIs, or sometimes called ports. For example, I could declare that I use SQL Alchemy to access database, or I handle some REST API requests at high level. At the configuration level, I need to perform some bindings to resources. For example, I could say I want PostgreSQL database with certain security protection like VPC or encryption. And I could configure REST API through API gateway endpoint and demand, again, particular VPC protection if required, or authentication, and other security measures. The infrastructure, this Python infrastructure from Python code will transform the logic code suitable for direct operation with Cloud SDK and produce automatically a template for deployment. How it could look like? It's vendor-specific example, but I'm mostly focused on giving you general understanding how it would look like. So here is an example of pretty straightforward CRUD service that manages to-dos. Get to-dos, create to-do, get to-do, update, delete, typical CRUD service. It's a pure Python code, as you could see. It uses standard collections ABC interface and doesn't mention cloud whatsoever. Nothing. And then that will be translated, I will show you certainly shortly, into, in this case, AWS Cloud Formation template with about 1 to 20 ratio of different resource definitions. How we accomplish that? We follow again 12-factor application recipe: build, release, run. At build stage, we transform original Python code, bind it to SDK calls, and produce template. At release, in our system, we just upload it to cloud storage, for example, S3. At run, we deploy cloud-produced Cloud Formation stack using this template, and that it will create all necessary resources. For example, DynamoDB database, maybe a workflow, step function, state machine, Lambda functions, API gateway, whatever is required directly derived from application code. It might look still for you a little bit abstract, so let's switch to live demo. Live demos, I know, are discouraged. So what we will do, I will one at a time go with you through code, and in parallel, I will launch our command line that will run the system. It takes about 5 minutes to do it. Most of the time is spent by Cloud Formation itself. So let's see. This is the same CRUD service code as I presented at slides. Nothing special about cloud. There's something cloud neutral, but not vendor neutral yet. I have to work on that. That provides configuration, and it says in this particular case, it says that in production mode, use DynamoDB, and in test mode, use blob storage. Now we have 2 tests. One to test it locally. This test runs completely local on my desktop, virtual machine on cloud, And it validates our logic. You even didn't mention how fast it passed. A couple of seconds. The second one will validate it in a remote test through REST API, really. As you can see, we have this authentication and REST API communication. What happens now? You see, we produce a CloudFormation stack in parallel. That's what happens in here. It's automatically created. From where it created? It created from, I need to open it. This is a produced template automatically, and this is modified Python code. While we were talking, it deployed the stack, and now it runs the remote test. Again, we could see here that all these resources were created automatically. And again, I said it's about 1 to 20 ratio between application code lines, line count, and produced template. Running remote tests takes more time because they communicate through internet and API gateway and authentication. So we normally prefer running local tests as much as possible. That's it, more or less. I mean, in live demo how it works, and it really works as smoothly as it is. Yeah, that's it. So what I need to do now, I need to shut it down to save resources. Let's come back to my presentation. Let's dive 1 inch, and it's a long discussion. I will give you only a kind of testing of that technology. In order to perform that transformation of logic and configuration in Python to cloud infrastructure, we need to address 4 concerns: how we acquire cloud resources, how we configure them, how we consume them through SDK, and how we operate them. And that needs to go per resource provided by different services. They could come from different vendors, and we could use multiple APIs to accomplish this task, and the result could be deployed at different locations. And that's what we know from the 3 most important things in real estate, right? Location, location, location. What I want to pick up your attention to, that cloud is very often incorrectly perceived as a kind of monolithic mainframe-like structure. It is not. It's a highly distributed system. We could deploy produced assets of our software starting from IoT gateway through 5G antenna tower, at CDN at on-prem location, for example, Outpost servers, and local zone. And central cloud in region, true. And every location has its own preferences in terms of advantages and disadvantages, in terms of privacy, latency, aggregation, flexibility, operation cost, and certain preferences for hardware, where ARM CPUs will shine, where Intel is required. And sustainability is going to be a very important factor for deployment location decisions. The story doesn't stop here. We could deploy computation, and as you can see, at multiple places. It's not just Lambda function. It's not just Docker container or VM instance. We could deploy some computations directly in workflows or directly in endpoint, or using, for example, Elastic MapReduce, Spark. The same is for data. We could keep data in multiple places. And again, sustainability is a very important decision factor. And we could exchange messages using different infrastructures, from PubSub to direct messages. And many options are available. The main point here is that it's going to be progressively harder to optimize these deployment locations manually. Just too many variables to juggle. And some automation is required. What we have today? Today we have about a dozen of vendors, some of them are here. And I highlighted those who are involved in compiling Python code to some runtime environment. This is the symbol for LLVM, CLVM binary code. As you can see, most of them are concentrated in Python compiler to Python runtime, with one interesting exception of Cloudflare, which compiles it to Node.js. The potential is much bigger because we could just compile Python code to Python runtime, but we could also extend it using C++, Rust, or Go. We could use Sterkin for performance optimization. We could use PyPy, and PyPy sometimes works better because of JIT compiler. We could compile Python code to Node runtime, for example, by using PyDide, or to .NET using PythonNet or IronPython. Or Jython. Jython I'm less certain about because it's stuck in 2.7 Python. But anyhow, there are multiple options, and if we compile Python code to different runtime, we could extend it using different languages. So the potential is much bigger here. And that leads us to interesting observation where infrastructure from code means domain-driven design and hexagonal architecture. We could argue that infrastructure from Python code takes upon itself compiling application control logic, dealing with ports API, and binding them to particular adapters through a platform SDK. But domain logic could be implemented in multiple languages using multiple runtimes. And we could compile application logic, and that's what we do, directly to workflow specification, step function, for example. We could communicate with our computation units extended through in-proc with the same language or binary languages, but we could also integrate them through out-of-proc sidecar integration with other runtimes without sharing the same memory. Right? That's what is important, including GraalVM and including Julia and Node and .NET and Java. And that gives us much larger number of opportunities of generating automatically cloud infrastructure while preserving solutions developed in other languages for other runtimes. So how far we could go is as far as there is a market for it. The potential is virtually unlimited. What is needed? Mostly to let Python be Python. Let's use a couple of examples. If we elicit DB connection protocol from PEP, from DB API 2.0 PEP, we could map that protocol to different cloud resources implementing relational databases, Aurora serverless on Amazon, Athena, Redshift, or Snowflake, or MySQL on GCP on Azure. If we elicit protocols from standard Python library, for example, Path protocol, we could implement very convenient and transparent object browser for cloud storage, for blob. For example, S3. The same could be applied to open source. If we elicit protocols for sentiment analysis, that could be mapped to managed cloud services like Comprehend of Amazon. Again, Amazon just an example. What we do need to work together is to find some standard schema for high-level resource configuration. I don't need to specify for relational database anything related to cloud, but I still need to some way to specify that it's MySQL engine, and I want data to be encrypted on REST with particular encryption schema, and I want the cluster to be protected in VPC, for example. I need some way to express it at high level of abstraction without diving into low level cloud details. So I could reformulate the objective of Python IFC. It's actually to unlock full potential Python as cloud-native programming language. We could adjust, adapt it, runtime, and compiler to work naturally with cloud infrastructure and using the binary extensions where appropriate. So, things to take away. The mission of infrastructure from code is to make cloud accessible to mainstream Python programmers. They have enough to do. They have enough to work on. And they don't need to spend too much time on learning or constantly changing low-level details of cloud infrastructure. Cloud is a computer. Template languages of orchestration engines on different clouds, think about them as a machine level language, like assembly. We need to be able to compile into it, raising up the ease of use in terms of development, deployment, and operation without compromising cost, security, and reliability. And that could be done. And it's not academic. I mean, it's not purely thought experiment we perform in our laboratories. This is an example of non-trivial, pretty sophisticated workflow. It's a step function state machine compiled directly from Python code using 3 parallel threads for performing IAM credentials validations, whether they are expired or near to be expired, and sending email notification to corresponding users, and blocking credentials if credentials are really expired. You may find more details or experience reports from our team on that site. The most recent one is from our CO, Chief Operating Officer, how we implemented through that infrastructure security scanning of Python libraries and Docker images, and all assets, artifacts coming from external world, increasing the level of security. That's all what I have for today. Questions I will take in QA room when I reconnect back to Ventureless service. Thank you very much for your attention, and I will upload my slides to SlideShare. That's it.